Hi, everyone, and welcome to the third lesson for the week of April 13th through the 17th. So we've been going through Newton's three laws, and today, well, we're going to get to the third law. So let's get started right away with the question of the day that, fortunately for you, you don't have to write down right now, but just kind of pay attention to it. What is Newton's third law? Well, the good news is I'm almost certain that you've heard about this law. It's by far the most quoted. It's the most popular of Newton's three laws. For every action, there is an equal and opposite reaction. It's so well quoted and so common that, in fact, that there isn't even a Mr. Jackson version. I couldn't think of a way to make that even simpler. So for every action, there is an equal and opposite reaction. That's what we need to get into today. So let's jump right into it. All right, oh yes, here we go. This unfortunate picture right here. All right, now for this one, here's a great example. You've got a train which would have a tremendous amount of force involved in it. So when it hits just, well, an old car, well, I don't know. Actually, it looks like there's a new sticker right there and everything. Maybe the car dealer decided to park the brand new car right there on the car tracks. It seems unfortunate. But anyway, when they hit, there's an equal and opposite reaction. For the tremendous amount of force that the car receives from the train, the reaction is the car goes flying away. All right, so it was a tremendous amount of force that was applied to it. How about this one though? All right, in these cases right here, you have two cars smashing into each other with they're the same type of car, or in this case, the same type of Jeep. Because they're the same type and they were moving at the same speed, well, the damage is similar, right? They receive almost identical damage to the cars because they have equal reactions for them. Oh, here's another unfortunate picture right here, right? If you have several football players all tackling, well, one football player, well, that's not equal, right? But the reaction is going to be the same, right? It's going to be the force of this player plus this player plus this player plus this player plus this player, all imparted to the one football player. And, the result's not going to be good for the one football player, right? Are you ready for the joke of the day? All right. Why do you think that Sir Isaac Newton was such a chill guy? Why was he known for being chill, cool, calm, and collective? Because he just seemed pretty down to earth to me. Get it, y'all? All right, so yeah, there's the joke of the day and everything. Oh yeah, and then there's a bonus joke of the day. Did you know that before he discovered gravity, way back in 1687, people could fly? I don't know. Sounds like a tabloid or something like that article. All right, let's kind of move on with today's mini lab. Now, for today's mini lab, sorry, if you could think of a way to do this at home, that'd be great. I really couldn't think of it because normally in school you have these little kind of mini rail tracks that I have right here and a series of spheres. So what we'll do is really quick, I have it right, let me center it, here we go, right down here and everything. So for Newton's third law, well, what we do is we call this a stringless pendulum. I've got some of those really, really heavy spheres right here. And then the spheres, they're made out of steel, and the steel is excellent at basically transferring energy, right? If I just tap it like the tiniest little bit, like that energy goes through this sphere, into this sphere, into this sphere, and then comes out on this one on the end. And so even with like tiny little taps, you can see that it goes through. You got to imagine in your head, right? When this one smacks into the next one, this sphere right here, it literally contracts in and then expands out, and that's what pushes the energy into this one. It contracts in, pushes out, and that's where this one, it contracts in, but it has nothing to push on, so that's why it rolls away, right? So they're great examples of Newton's third law, and if I pull back and let it go, you can see what happens, right? It's showing you that equal and opposite reaction. If I pull back two of them, right, well, then the reaction is going to be, did you see the break? Two, right? There's going to be two if I pull back on this side. Hold on here. Then there's two, right? It's always going to be the same. If I pull back three, let's see if we can show it right here. Stop moving. Stop moving. Three, right there. I saw it. Three, right? Let me try it on the other side one last time. If I pull this back, and we have three of them slamming in, right there, right? There was three. So the reactions are going to always be the same between them and everything. Right? Let me show you this guy right here that I show you normally in class. Do you ever go to Hershey Park? At Hershey Park, if you go on the Storm Runner, I believe is the roller coaster that you do, this is one of my favorite roller coasters, right? Because for this roller coaster, well, it starts out somewhat normal as far as you get in the train, right? The train kind of goes down before you get to the hill out there in the distance. You can kind of see this hill that's going on, right? But what happens is down here, well, they're kind of gone now, but they were really, well, right here, this track right here, these are all super, super powerful magnets. So when the ride starts momentarily here, what happens is the magnets push you ahead, and you're like, ah, the wind messes up your hair. You can imagine my hair flying through the sky. You go over the big hill right here, you go back down, right? This is all Newton's laws that we talked about on roller coasters earlier in the week, right? You're spinning around, you're spinning left, you're spinning right, but there's so much momentum that the train keeps going around swirls and everything like that. So much so that at the end of the ride, coming up after this turn right here, they actually have to have more, you can see them right there on the tracks, more magnets, right? And the magnets actually have to slow the train down because it had so much momentum as it went around, you know, that roller coaster ride, right? So that's Newton's third law right there. Or how about this for an example for Newton's third law? Do you ever want to hear the entire history of all warfare up to, you know, today's date and everything like that? Well, it started out with someone being mad at someone else, so they threw a rock, right? They moved up technologically to, you know, slingshots, you know, to be able to throw. Now you can throw the rock much further, much faster. They moved up to bows and arrows, right? And then eventually, you know, we got gunpowder as human beings and everything. And, you know, that's where we're, you know, that's where we currently have been and everything. But did you know there's a fifth main version of a way to basically throw things at people and everything? But think about it. Up until now, the history of war is still the same. Someone's, you know, got something, you don't like somebody, so you throw something at them, whether it's a rock, a faster rock, an arrow, right, or some kind of metal projectile, you know, that you're shooting out at it. But there is a newer version where they use magnets, similar to that roller coaster ride. Well, of course, you know, some people think of ways to turn that technology, you know, instead of being for good, for bad, right? And what they use is a series of super, super powerful magnets, just like they did at Hershey Park. They put a projectile in there and they force it out at extremely fast speeds, way, way faster than any normal gunpowder could use, right? So they can, you know, transfer, you know, things very, very fast, right? So we're talking several times the speed of sound here and everything. Because of that, it can go much further too, right? So that's it's called a rail gun. And normally we have like a little mini version here in class that I would show you, but I don't have that. I didn't bring that home with me. Okay, the vocabulary word for the day is momentum, right? Newton's third law is often called the law of momentum, right? So for momentum, what we're doing, instead of writing it down, you don't have to worry about writing anything down in your workbooks anymore, right? But basically, it's the product of an object's mass and velocity, right? So to figure out the momentum of an object, what you need to do is you need to figure out what the mass of it is, how heavy the object is, and multiply that by the velocity, what speed that it's going at and everything. So an example could be, let's say you have a toy car, right? It's moving at 10 meters per second, right? If the toy car was 5 grams, how would you figure out its momentum? That could potentially be a quiz question coming up in just a few minutes here for you, right? So you need to know two things. You need to know the mass of the object, in this case, 5 grams, and you need to know how fast it's going. In our case right here, 10 meters per second, right? So if you multiply the two of those together, you get 50 grams meters per second. That's the momentum, and that's actually how you say it, 50 grams meters per second. So you keep, you know, the, you know, however massive the object is, you keep whatever velocity the object has. So 50 grams meters per second. That would be the example that you could have for it. And then, oh yeah, there's a funny short little thing right here. Here's a great example of momentum. Oh my goodness, someone being hit in the face with a soccer ball right there. Oh, you know, you don't realize, you know, if you're playing something as simple as soccer, you're thinking, oh, that soccer ball is kind of soft, that won't hurt or anything like that. But here we go in slow motion right here. Oh, first the ball kind of smooshes in, but eventually all that momentum is transferred to the dude's face here. And watch his nose is the worst one. Oh, his nose, that's just gross right there. I mean, his whole entire face is all like squished up as the energy's transferred into his face, right? But there's a great example. For every action, there's an equal and opposite reaction. Newton would be so proud of this as a third law. All right, that's kind of disturbing. All right, let's move on here and everything, right? So if let's do this one as an example, just in case this was a quiz question. Well, maybe it will be. Maybe you're rewinding to see this and everything, right? If a soccer ball has a mass of 150 grams, let's say, right, and it's traveling at 12 meters per second, what's its momentum, right? So it's 150, right, grams times 12 meters per second. So you're going to get 180 grams meters per second. That's the way that you would calculate that out, right? So that's, you know, that's the way you can calculate it. Now, for Newton's third law, right, what that means is there are two things to figure out how much momentum an object has, right? It's how heavy it is and how fast it's moving. So let's take, for example, right, I've got, the big sphere in the picture right here is one of these really big, heavy, spheres that I had. Then the middle one, well, that's probably an average size, ball bearing that you might have. And then the little tiny one down here, well, that's literally from a BB gun, right? That's like a BB that we have and everything. So the question would be like, which one of these do you think would have the most momentum, right? The smart student among you is probably, or hopefully thinking, it's a trick question, Mr. Jackson. They all can have the same amount of momentum, right? It all depends on the speed that they have. Even though this one's really, really heavy and massive, this one's kind of in the middle, and this one's almost nothing there at all. They can all have the same amount of momentum, right? What if this one's rolling really slow, but this one's rolling much, much faster, right? They can have the same amount of momentum, right? And then what if this one's going really fast? What if this one's shot out of the actual BB gun and everything? So if you had an object, I didn't plan ahead of time here and everything. Let's say you have the stormtrooper right here, right? If you have your stormtrooper and you want to knock him over with one of these three spheres that are right there in front of you and everything, which one would do the best job? Well, the answer is all three of them could do equally as well, right? Because you could have the really heavy one hitting them really slow, this one hitting them kind of at a medium speed, and even the little tiny one that you might think, oh, if I just throw that little BB at the, plastic stormtrooper right here, nothing's going to happen. But what if you fire it out of the BB gun? It's probably going to knock them over as it goes right through them and everything, right? So momentum, how much energy the object has while it's traveling, it depends on how heavy the object is and the speed that the object's going at and everything. And then the ultimate example of this is Newton's, the Newton's cradle, which I'm going to cut to right now really quick to show you an example of Newton's third law with. Hi everyone, here we are with the giant Newton's cradle. As you can see, it is a much better example of Newton's three laws than the little baby old beat up Newton's cradle that I've been showing you earlier. The first example right here of Newton's third law is by pulling back one of the spheres, well, you can see there's an equal and opposite reaction. Each time that sphere slams into the first sphere that's just sitting still, it transfers its energy to the next one, and then to the final one. That energy sends the final one shooting out, which then just repeats the entire process again. Right? So that's Newton's first law. For every action, there's an equal and opposite reaction. Here, though, we pull back two of the spheres, and you can see the same thing happens that was going on before, as far as the energy is transferred through the spheres that were just dangling still, but this time it's transferring twice the amount of energy because two balls were pulled back. So twice the energy goes through the middle ball, twice the energy goes through the next to the end ball, twice the energy goes into the far one on the far right-hand side in this case, and then the process starts all over. Those last two have all that energy, so they swing out, and then they go back in and smack into the middle one, and then the whole process repeats itself again. But according to Newton's third law, what happens if we pull back three of the spheres? Well, in this case, I'll pull back three of the spheres, so now you have 3 times the energy is transferring. This time there's so much energy that it transfers into the other 3 spheres, and then they swing out to the right-hand side, and now that begins the process all over again. So again, it's Newton's third law. For each action, there's an equal and opposite reaction. So if I pull back 1 sphere, well then 1 sphere on the opposite side ends up swinging out. If I pull back 2 spheres, then 2 on the opposite side swing back. If I pull back 3, then 3 do. But then the ultimate question is, what happens if I pull back not 1, not 2, but 4 of the spheres? Well, same thing according to Newton's third law, right? Equal and opposite reactions. So much energy transfers through that 4 of the spheres swing out to the right in this case, and then that energy transfers back to the next one. That's Newton's third law. For every action, there's an equal and opposite reaction. Okay, that was cool, right? I mean, that was fun because you could see it much, much better than, remember that little tiny Newton's cradle that I had? I mean, that thing is, I mean, it's got to be put out to pasture here eventually and everything for us. Okay, the grand finale of the lesson for today is going to be this short little video right here. We're going to send off our Newton's cradle with a bang right here, all the way from Great Britain is this short little video right here. It shows you what not to do with your microwave, especially during, these hard times and everything. So after you watch this video, What you want to do is there's another short video that you can click on from the European Space Agency, right? For example, is about Newton's third law. And then after that, there's going to be a short quiz for you to take, right? So you'll take the quiz about Newton's third law. Let me get this guy going for you.
Stop. The following experiment is dangerous. Do not try this at home. No, really, don't.
Great ball of fire!
The Newton's cradle, named in honor of Sir Isaac for exemplary work with apples and designed to illustrate the conservation of momentum and energy. And the microwave, designed to illustrate that obliterating food into a tasteless mess doesn't have to take all day. But what happens when you combine the two? Shiny steel balls deflect the microwaves, producing sparking points as the radiation flies off back into the oven's shell, which in turn causes havoc with the oven's magnetron, until it's finally too much to bear. Another good reason not to put metal inside a microwave. We do these experiments so you don't have to. Do not try this at home.
All right. So don't try that one at home, and make sure to try to stay safe.